Good day, students. So welcome to part 5 of our differentiation review flashcards. We are going to be going over formulas 20 to 25. In this installment, we're going to be taking a look at the derivatives of exponential, logarithmic, and absolute value functions. Do visit our website at mathgotserved.com for access to a wide variety of tutorials ranging from algebra all the way to calculus. Now let's take a look at formula 20. This is read, the derivative of the natural logarithm of u. This is ln, it's not 1n, okay? This is ln of u. So the derivative of the natural logarithm of u is 1 over u du dx. Remember, the du dx component is a consequence of the chain rule, applying the chain rule to this composite function here, ln u. Notice u is not x. This is representative of a composite function, okay? So the derivative of ln is 1 over u times the derivative of the inner function, which is du dx. Let's take a look at an example. The derivative of the natural logarithm of the arctan of x. The outer function is the natural logarithm. Arctan of x is u, the inner function. So if we apply the chain rule, we'll have 1 over u, or 1 over the arctan of x, times the derivative of the arctan of x. In part 4 of our review installment, we found out that that derivative was 1 over 1 plus x squared. So when you multiply 1 over arctan of x with 1 over 1 plus x squared, you have 1 on the numerator, a result of multiplying 1 and 1. In the denominator, you have arctan of x times 1 plus x squared. An example of the application of the differentiation rule for the natural logarithmic function ln. Formula number 21. This is a derivative of log u base a. The derivative of log u base a is 1 over u ln a du dx. Let's take a look at an example of this. The derivative of log 5x base 3 is 1 over u is 5x, so it's 1 over 5x ln of the base, 1 over 5x ln 3, times the derivative of the inner function, which is 5x. The derivative of 5x is 5. That's multiplied to the numerator. And you notice that these two 5's cancel out, so you have 1 over x ln 3. This formula is a special case of the other formula we just looked at, ln. In the case of the natural logarithm, the base is e. So when you take the natural logarithm of e, that piece falls off since you're inverse functions, and you're left with 1 over u. That is why formula number 20, the derivative of ln u, was simply 1 over u because of the ln e that canceled out. All right, let's move on to formula number 22. The derivative of e to the u, the exponential function. The derivative of e to the u is e to the u du dx. The unique thing about this function is it is its own derivative. All right? Let's consider an example. The derivative of negative e to the cosecant x. This is a composite function. U is cosecant x in this situation. So we can factor out the minus when we differentiate e to the cosecant x. We end up with e to the cosecant x just as e to the u. And then we differentiate u, which is the derivative of cosecant x. The derivative of cosecant x is negative cosecant x cotangent x. So that negative, we can factor it out to multiply by the other negative that's present in the problem. So we have positive e to the cosecant x cotangent x. An example illustrating the derivative of the exponential function e to the u. Formula 23, we have the derivative of a to the u, okay? The derivative of a to the u is a to the u ln a du dx. This is also similar to the e to the u situation. The e to the u situation is a special case of the a to the u formula. When you have e to the u, you have e to the u here times the natural logarithm of e, which is the base, and those two cancel out, and you're just left with e to the u. That's why the derivative of e to the u is e to the u as illustrated in formula number 22. So these two are connected. Let's consider an example. The derivative of 5 to the x to the third. In this case, u is x to the third. So its derivative is going to be 5 to the u. U is x to the third. ln a, the base is 5. So ln 5 times the derivative of u, which is x to the third. If you apply the power rule there, you're going to have you're going to have 3x squared. Okay, this can be simplified, rewritten a little bit nicer, but this basically captures the application of the differentiation rule of an exponential function base a. Now let's take a look at formula number 24, the derivative of root u. Now, this is just a shortcut. Remember, root u can be expressed as u to the 1/2, and then you can apply the power rule there to find the derivative, but this is a shortcut, basically summarizing the application of the power rule and the simplification process that you have to do after that. So the derivative of root u, shortcut, is 1 over 2 root u du dx. This is a very handy formula to have or to know when you're differentiating radical functions. The derivative of 5 root ln x is an example. We have a composite function here being multiplied by 5. You can factor out the 5. And when you differentiate the composite function root ln x, you can apply this formula. You're going to have 1 over 2 root ln x. U is ln x in this situation. And then you're going to multiply your final result, 5 over 2 root ln x, with the derivative of u, but u is ln x. So the derivative of ln x is 1 over x, as we went over earlier. And then you multiply 1 over x with 5 over 2 root ln x, and you have this result right here, 5 over 2x root ln x. An example of the application of the differentiation rule for root u. All right, let's take a look at the last formula in this flashcard series, the derivative of the absolute value of u. The derivative of the absolute value of u, this is an interesting formula, is u over the absolute value of u du dx. Let's take a look at an example. What is the derivative of the absolute value of sine 3x? So in this function, again, we also have the composition of 3 functions. So we're going to be using the chain rule twice for the absolute value function, and then for the trigonometric function, and then we will differentiate the 3x without applying the chain rule. So in this situation, when we're working on differentiating the absolute value function, u is going to be sine 3x. So the absolute value of sine 3x will be equal to the absolute value of u. The derivative of the absolute value of u using the formula is u over the absolute value of u. If we input sine 3x in there, we're going to have sine 3x over the absolute value of sine 3x as illustrated in this portion right here. Now to differentiate sine 3x, that's also a composite function. U is going to be 3x. So the derivative of sine 3x is going to be the derivative of sine u. The derivative of sine, we know, is cosine. So it's going to be cosine u times the derivative of u. U is 3x. The derivative of 3x is 3. So when you put everything together, you will have the derivative of the absolute value of sine 3x being 3 cosine 3x sine 3x over the absolute value of sine 3x. All right. This is an example of the application of the differentiation rule for the absolute value function. So thanks so much for taking the time to watch this presentation. Remember, you can use all these formulas to generate flashcards and then go over them over and over again until you master them completely. Do subscribe to our channel for updates to other tutorials to aid you in completely mastering calculus. Also post a comment to let us know what you think about this tutorial or to make requests as to the kinds of tutorials you would like to see. Do give us a thumbs up or favorite this clip if you liked it and share it with your friends. More clips can be found on math.serve.com. Thanks again for watching and have a wonderful day.